Hi, my name is Ricky Stevens, and this is my project report on coffee mug optimization. For this project, I would like to find out what is the optimal mug shape that will minimize the heat transfer from the coffee to the surroundings. I will make the following assumptions to simplify this problem. I will assume that the heat transfer is steady state, so the coffee remains a constant temperature. I'll also assume that the heat transfer is one-dimensional through the mug. I will ignore any evaporative cooling and ignore the complex geometry of the mug handle. I will also assume an axisymmetric mug design and assume that the mug is completely full of coffee. To formulate this problem, I will represent the different possible mug shapes by slicing the mug into a number of cylinders, each with height dz and independent radius ri. These will be the continuous design variables for the problem. The objective function, which is to be minimized, will be the total steady-state heat transfer rate from the coffee to the surroundings. I will consider the three modes of heat transfer from the top, bottom, and sides of the mug, using a thermal resistance model analogous to Ohm's law for electrical systems. Here, the equivalent resistance of the system will be a function of the different areas through which heat transfer is taking place. These areas can be expressed in terms of the design variables, which simplifies this problem to a continuous, nonlinear programming problem that can be solved in MATLAB. Here is the thermal resistance model I developed for this problem. The equation for the equivalent resistance of the entire system is shown below. I noticed that coffee mugs have this ring on the bottom to minimize heat loss to the table by conduction. I decided to include this ring in my analysis. Here are the formulas for each resistor along with their descriptions. As I mentioned before, the thermal resistance is a function of the thermal properties and the relevant area through which heat transfer is taking place. These are the equations I developed for the relevant surface areas of the mug. They are functions of the design variables and constants I defined, such as the constant wall thickness, T. Plugging in the area and resistance expressions into the objective function, I developed this long equation for the total heat transfer rate from the mug. This is the objective function for a mug with 4 slices. For more slices, the expression gets much longer. These are the constraints that I defined for the problem. The volume constraint is an equality constraint, while the rest are inequality constraints. The open top constraint simply requires the top of the mug be wide enough to drink from, while the stability constraint requires that the bottom be wide enough so the mug won't tip over easily. The inward overhang constraint limits the slope of the inward leaning sections so the mug is easier to drink from. Lastly, we have the bounds on the design variables. Here are the optimal solutions I found using fmincon in MATLAB. I ran the script for 4, 10, and 20 slices and saw an improvement of the function value as the number of slices increased. The shorter design, shown in blue, is the optimal design I found, while the taller design in orange was slightly worse, but still pretty good. As n goes to very large numbers, I expect these designs to smooth out and their function values to approach their converged result. I decided to see how accurate my assumptions of one-dimensional heat transfer were by comparing my model with a finite element simulation. I designed this simple cylindrical mug with a ring on the bottom and compared the total heat transfer rate from each surface. Comparing the total heat transfer from the mug, my model had a percent error of about 11%. The one-dimensional resistance model was a very good approximation of the heat transfer through the side of the mug because the thickness is much smaller than the radius. The approximation was not so good for the ring at the bottom because the ring in this model is all the way at the bottom edge, diagonal from the coffee, and heat will leak out of the sides of the ring. Thus, the 1D resistance model overestimated the heat transferred to the table. This project has enabled further research, such as investigating the convergence of these designs at larger n values. We could also consider transient effects, such as the heat capacity of the mug material and how the table or coaster beneath the mug heats up over time with different materials. Thanks for watching.